blood into the aorta, we see the average high of 120, and then when the ventricles and aorta are relaxed, we see the average low at 80. So this is showing the fact that we have a reflection of the diastolic and systolic changes. Once we get past the capillaries, we no longer see that. All right, so you're not going to be able to detect a pulse in the veins, not because there's no pressure there, but because there's no expansion. And what we feel as palpated as the pulse is the expansion from the volume of blood with each stroke volume. In the veins, it's just a constant pressure flowing through, and so once we get to that area, we no longer, past the capillaries, we no longer see that. So what is going to then affect how this pressure is obtained? And we have two factors that are going to contribute to changes in blood pressure. Cardiac output, which in my normal schedule we would have already covered, all right, and peripheral resistance. So cardiac output we're going to look at first is how that's controlled. We've already covered a lot of that. And what the definition is, peripheral resistance is, so cardiac output is the volume of blood that's going into the vessel walls, and as you can tell, a greater volume is going to stretch the walls greater, and they're going to resist that stretching. So it's going to increase pressure, push more volume pushing against the walls. Resistance is the physical effect of the water molecules and the proteins and the blood cells flowing against the surface of the blood vessel walls. So peripheral resistance is going to be related to surface area. In a particular blood vessel, there's a cleaner flow in the center of the vessel. It's called laminar flow if you take physics, and an increased turbulence as the molecules in the water or the blood are bumping against the surface wall. So the larger diameter we have, the less the proportion of that overall molecular components are actually coming in contact with the surface of the vessel. And the greater the proportion of the fluid is in laminar flow. If we have a lot of smaller vessels, we're getting a greater proportion of the fluid in contact with the vessel walls, and therefore a greater effect of surface area. Okay. So those two factors we will follow as to how they're going to affect blood pressure. The first one we're going to look at is cardiac output. We've been referring to this in terms, but let's actually define it. And cardiac output, or CO, is a minute flow volume measurement. So when we talk about cardiac output, we're talking about the volume of blood that one ventricle, not both of them combined, that one ventricle pumps out in 1 minute. So that's why we have heart rate, because the heart rate is measured in beats per minute times stroke volume. And the stroke volume is volume per beat. Or you could say strokes per minute. Right? So if one contraction, and this is one ventricle, all right? So we're looking at the cardiac output of one ventricle. Would it matter which one we measure? Is that going to change the volume? No, because remember, as a healthy heart, volume is going to be the same. Pressure will be different. All right? Lower pressure into the right for the lungs out of the pulmonary trunk, then out the aorta, and the difference in the thickness of the ventricular wall. But volume with a healthy heart should be the same. Otherwise, we get congestive heart failure and different volumes, we end up with problems. All right? So heart rate times stroke volume. Typically, heart rate, and you'll see anywhere from 72 to 75. Math-wise, it's easier for me to just say 70. Stroke volume, 70 mils. So that comes out to approximately then 4,900 mils or 5 liters of blood per minute. This is about what you have in your whole body. All right. Now, you can see that if we pump out a greater volume, and we discussed this already earlier, if we have a very strong heart and we pump out a greater volume, the heart doesn't need to beat as often. So if we're pumping out 100 mils to get 5 liters, we only need 50 mil. Do it backwards here. If we're pumping out 100 mils of blood with each force, it's almost a third more, we only need 50 beats per minute. If you look at it another way, and we have less volume of blood, so we have less blood returning to the heart because of hemorrhage or dehydration, not drinking enough, too much sweating, therefore our volume has dropped, so we're only pumping out 50 mils. Then to get the same adequate perfusion pressure, blood pressure, heart rate needs to compensate by going up. Okay? So with these numbers being the same, cardiac output is going to be the same, but within that we can adjust either higher heart rate or higher stroke volume or vice versa. Okay? So let's look at, we've already discussed when we were talking about autorhythmic cells, we've already discussed the factors that affect heart rate. So let's just review those. So heart rate is going to be affected by the autonomic nervous system. And remember, we have a tonic, acetylcholine, sympathetic nervous system, vagus nerve that decreases our pacemaker rate from 100 to an average of 70 beats per minute. And if we decrease that or cut that back, heart rate's going to go up. Or if we add more acetylcholine, we're going to slow the heart rate even more. Okay? So this diagram over here on the right is showing those two components of the autonomic nervous system. So vagus has its preganglionic cell bodies in the medulla, in the cardiovascular center, and that can be affected by change in oxygen content. It can be affected by change in pH, by emotions. This proprioceptors from your joints, as you start to stretch them before you even need more oxygen, will send the vagus nerve branches primarily to the SA node and AV node and to atrial muscle, all right, to the atrial contractile cells. We do not see parasympathetic fibers going to ventricular contractile cells. So the parasympathetic effect will be seen in heart rate and to a small degree on the force of atrial contraction. Sympathetic fibers go to those same components as well as the AV bundles and ventricular contractile cells. So it is the sympathetic nervous system that's going to affect the force of contraction. So if we have a stronger contractile force or a weaker contractile force directly due to innervation of the muscle cells, that's going to be due to the sympathetic nervous system. So again, this isn't anything new. Here's similar to what you saw in the cadaver earlier. Vagus nerve is coming down on the left and the right side and forms a plexus, sends its fibers in, and are found primarily on the SA, AV nodes and on the atrial cells. And its role is going to be to decrease our heart rate, increase the TP interval. Again, this is a review of what we covered on the physiology. So acetylcholine binds to muscarinic receptors. Remember, nicotinic are ion channels, muscarinic are G protein. And we have two G protein types that can be activated. The inhibitory type decreases adenylyl cyclase activity so that we have a decrease in cyclic AMP. And with a decrease in cyclic AMP, We have fewer funny channels opening, and they open later. Again, so the cell is more hyperpolarized, and fewer of our transient calcium channels open. So the overall effect of the inhibitory is to start the so we have to, if this is our normal location where we start opening our funny channels with acetylcholine, we go a little bit lower, hence we have more positive ions that have to enter the cell to bring us up to the same starting point as our typical resting heart rate. And then we have the excitatory G proteins that open potassium channels. All right, so these would be ligand-gated channels. And not only then do we start, like, you know, putting somebody behind the starting line for a race, handicapping them, but we're also hobbling them by tying one foot up to their leg, and they have to hop instead of using both legs. So while positive ions are coming into the cell and the cell is depolarizing, with open potassium channels, we're also losing positive ions. So if this line is going like this, what the effect of acetylcholine is it lowers that gradient, makes that gradient more shallow. So between those two effects, it takes longer to reach threshold. Okay. Does that seem a little bit familiar, hopefully, from what we talked about with our autorhythmic cells? So we're talking about the effect of acetylcholine on autorhythmic cells, because we're looking at heart rate. Okay? Heart rate times stroke volume affects the cardiac output. So we're looking at that first component. So this is going to be a decrease in heart rate. If nothing else changes, and that's the tricky part, right? So if nothing else changes and we decrease heart rate, what would be the effect on cardiac output?
Decrease.
It's going to decrease. Now obviously, if we have a healthy heart, it's going to compensate by increasing stroke volume. All right, we'll talk about stroke volume in a moment. But when I ask these questions, I want what's the effect of acetylcholine binding on cardiac output? I don't want you to think of all the compensatory mechanisms that occur, but it's the direct effect. Lowering heart rate is going to lower
Cardiac output.
stroke, cardiac output. All right, so don't start adding in compensatory mechanisms. I want the first direct effect. Okay, the sympathetic effect on the heart is coming off of, they're not named nerves like the vagus nerve, they're just called cardiac accelerator fibers. Coming off of the sympathetic chain, they actually go up to the cervical ganglia first and then come down to the heart. So again, beta-1 receptors. When we talk about heart rate, we're talking about SA node and AV node, but we also have receptors on the contractile cells. So unlike acetylcholine, norepinephrine can affect stroke volume. But again, right now we're looking at heart rate. Okay, we'll come back and look at norepinephrine for stroke volume in a moment. So beta-1 receptors bind norepinephrine, and as you saw, it activates adenylate cyclase, which binds to our funny channels, and more sodium is coming into the cell. It also binds to the transient calcium channels, and more calcium comes into the cell. Both of those are going to cause this effect. So we reach the funny channels open earlier. More of them are open, and more of our transient calcium channels are open. So we have and I've exaggerated there, but we start earlier at a higher, more positive level, so it doesn't take as long to reach threshold for the autorhythmic cells. Plus, with a steeper gradient, more positive ions are coming in at a faster rate, and it takes less time. Okay? So if we go back to the earlier slide, here's our normal value. The only thing wrong with this slide is it has everything starting depolarization at -50, and that's not true. For our parasympathetic, it's going to start at a -70. For our sympathetic, at around a -40. You don't need to memorize those numbers, but one's higher, one's more negative, one's more positive. Sympathetic is going to start depolarization more positive. Membrane potential, parasympathetic is going to start at a more negative. So this is inaccurate here. But you can see that we have a steeper gradient, and we have more action potentials per minute with norepinephrine, a more shallow gradient, and fewer action potentials per minute. Right? It's the net effect of the two different components of the nervous system. Okay, hormone effects. Thyroid hormone functions to increase heart rate. This is where my headache kicked in last night. I was trying to get some images that would show it a little bit better. Typically, most of the articles that I read left it at thyroid hormone increases the oxygen need by the body because it's making more ATP. Therefore, it increases heart rate. But it actually does affect genes within the autorhythmic cells. And so it causes changes in the receptors. More receptors are present. More funny channels are made. All right, and other pacemaker regulation genes that occur. So remember, thyroid hormone is not a steroid, but it actually goes into the cell. And like a steroid, it can have change the genes that are being transcribed as well as have other effects. Okay, I'm not going to ask you specific questions on these. It's a little bit more detailed than we need in this class, but I just wanted to give you an idea that it's more than just changing oxygen demand for the body. Okay. Estrogen, this is what really gave me a headache. Estrogen decreases heart rate. So all the articles I was reading were talking about treating postmenopausal women with ERT and its effect on cardiac disease. I couldn't find anything really specific, but a couple of things. It has an effect on the calcium channels, and nitric oxide is going to dilate blood vessels for a greater volume so the heart doesn't have to beat as much. But basically, estrogen decreases heart rate. Cortisol increases. Notice I didn't put any reason down there. I couldn't find any reason, except that the stress is going to affect and cause increased norepinephrine release. The thyroid hormone increases, estrogen decreases, cortisol increases. And then we have a case study today that looks at ion concentrations. Potassium hyperkalemia, in the case that we have murder by poison, was thought the potassium was used. Let me go through this with you, all right? You don't have to know this level of detail. I just got into it. So I didn't have this material last semester. It just was cool to see the changes in explanation. This is a normal ECG. And this is showing normal potassium levels are 3 to 5 milliequivalents. This is the change in ECG with a milliequivalent of 7. You notice the P wave disappears as it gets up to 8. As it gets to 10, we start to see a rounding of the T wave any higher. And we see it just becomes this kind of rolling wave. And that indicates that ventricular fibrillation and death are imminent when that appears. Okay? So I thought that was cool to be able to see those specific changes with increased levels. Now, the first part of the explanation is easy to understand. Remember, in the nervous system, if we increase the number of potassium ions outside the nerve fiber, and we open potassium channels, we have more potassium inside the cell than we have outside the cell. As we increase the potassium ions outside the cell, what's going to happen to the rate at which potassium leaves the cell?
Slower.
It's going to slow down because it's going to be repelled both by the positive charges and by the fact that our gradient is becoming more shallow. All right? So you see that with this right here. The dotted line is showing the increase in the positive charges inside the contractile cell. It's also going to be present inside the autorhythmic cells. Okay? The rest of this has to do with our contractile force. I'm not going to talk about it just yet. I'm going to save it for about 5 minutes and come back to it. But this first rise of potassium inside the cell is going to make the cells more irritable and more likely to fire. All right, as we look at our autorhythmic cells. Interestingly enough, it actually in our contractile cells will slow down, not slow down, but will decrease the effectiveness and eventually the heart stops. So it's really, it's really cool to see how we first increase the irritability but then actually stop the heart, and it has to do with our sodium and calcium channels. So we'll come back to this when we look at contractile components. I'm going to come back to that too. All right, so stroke volume. The cardiac output was half of the cardiac output was heart rate. All right. The other part of cardiac output is stroke volume. The cardiac output is, again, let's go back to that. I'll just write on the board up here in the corner so that you remember. Cardiac output is equal to stroke volume times heart rate. And heart rate is regulated by sympathetic and parasympathetic. So parasympathetic is going to decrease heart rate. Sympathetic is going to increase heart rate. Thyroid hormone is going to increase heart rate. Estrogen is going to decrease heart rate. Cortisol is going to increase heart rate. Potassium ions are going to first increase and then decrease and then die. Okay. Stroke volume. Stroke volume depends on the contractility of the heart, the ability of the wall to contract. Two things are going to affect that. One is the actual contraction of the cells, all right, which is going to depend on how much calcium ions are available. So remember the relationship with calcium ions, binding to troponin. The troponin moves, actin and myosin bind, and pull. Okay? So the more calcium we have, the greater the force of contraction. So that's the effect that we see here with the sympathetic nervous system. The sympathetic nervous system is going to function to increase the amount of calcium ions that the cell has. And it does so by, put that on the board here.
Did you say increases calcium or potassium?
Calcium. So it's going to increase intracellular calcium. Remember when norepinephrine binds to its receptor, so norepinephrine, epinephrine will bind to their receptor. That's going to result in the alpha G protein subunit activating adenylyl cyclase. Adenylyl cyclase is going to take ATP and convert it to cyclic AMP. Cyclic AMP will bind to long-lasting calcium channels and open them as we have our action potential formed. And we're going to get more calcium inside the cell. Most of the calcium calcium in cardiac contractile cells comes from extracellular calcium storage. All right? In addition, cyclic AMP is going to activate protein kinases. Protein kinases are going to phosphorylate, meaning add a phosphate group to calcium channels in the sarcoplasmic reticulum. And so we add intracellular calcium to our cell. Sorry, this is so low on the board.
Is this opinion varied? I noticed on the quiz it said that most of the calcium used is from extracellular, but then
Because there's a poorly developed sarcoplasmic reticulum in cardiac cells.
okay, I was just curious because on a couple of articles I saw it said it was like the 70-30 ratio, where it's 70% came from inside the cell and 30% outside.
Okay, show me, because the cardiac muscle cells just don't have as much of a sarcoplasmic reticulum as skeletal does.
Okay.
All right, so adding more is going to also, norepinephrine functions by not returning, by affecting the rate at which calcium leaves the cell. So we have additional calcium from that component. Now, yes, contractile cells. Yeah, so when we talk about stroke volume, we're talking about contractile cells.
There's only sympathetic nervous system
Right.
affects contractile cells.
Correct. And we're talking about ventricular contractile cells, because that's what's the most thing that's affecting our ventricular force. Okay, venous return. Venous return, the greater the amount of blood that returns to the heart, the greater the ventricles are going to be expanded. So here's the volume, here's the ventricle, okay, myocardial wall formed by the rubber band, space in there is the ventricle. So then as we get increased venous return, the ventricle expands. All right, we saw that with our ventricular volume on the graph of the cardiac cycle. There is a phenomena that says the greater the expansion or the stretch of ventricular muscle fibers, the greater the force with which they will contract, which has to occur. Because if we stretch out here, we contract the same amount, we're not going to move that blood out. So greater volume of blood will come in, and we only pump out the same amount. We're going to gradually overstretch the wall. So this refers to venous return. So increased venous return is going to mean an increase in end-diastolic volume. Do you remember that term? When we were talking about cardiac cycle, and down at the bottom of the diagram of cardiac cycle, we saw that we gradually increased ventricular volume until we reached end-diastolic volume when we were in isovolumetric, both valves closed. So that was our maximum volume. And then when we started the ventricular ejection, we lost ventricular blood until the semilunar valves closed. And then we were at a given amount in systolic volume. All right? So the maximum amount of blood that the heart will contain, can contain, but does contain with any given cycle is known as end diastolic volume. That's the end of relaxation. When the atrial valves close, atrioventricular valves close, and semilunar valves have not yet opened. That's what end diastolic volume is. So at the beginning of isovolumetric contractions. So in any of our isovolumetric periods, all the valves are closed. So the AV valve, semilunar valves are closed. And at the beginning of ventricular isovolumetric contraction, the AV valves close. No more blood is coming into the ventricles. That's our maximum volume for that cycle. It's the end of relaxation because now our ventricles are contracting. That's what closed the valve. So it's the end of relaxation. So end diastolic volume is the maximum amount of blood for that cycle in the heart. Pressure continues to rise and the semilunar valves open. As soon as the semilunar valves open, we see a decrease in ventricular volume. Does that make sense? It's being ejected into the aorta. All right? That stops when the heart relaxes and the semilunar valves close again. So this is the beginning of isovolumetric relaxation. The end of contraction, and so this is volume is known as end systolic volume. And that's the lowest volume in the heart. Okay? It sounds backwards because you would think systole we would have a great volume, but remember it's the end of systole. So it's the end of contraction. We pushed the blood out. Now the semilunar valves are closed and no more blood can leave. So that is maximum and minimum. However, blood volume is actually here. So on average, the heart's going to hold, each ventricle is going to hold about 135 mils. We pump out about 70. So we're not completely emptying the heart. Right? Now, if we increase venous return,